We talked about precipitation reactions, where reagents combine, ions combine, and lead to a solid falling out of solution. We've talked about acid-base reactions, where something carrying a proton and something usually containing a hydroxide ion interact to neutralize, to form a water molecule and something else. And we also mentioned redox reactions. So let's take a deeper, close look at redox reactions. Redox reactions involve the exchange of electrons. So if you take zinc metal and you react it with a copper +2 solution, you can generate solid copper. This is a stereotypical redox reaction. It involves the exchange of electrons. Now, in this example, it's much easier to see the electron change. This zinc has no charge. This copper has a +2 charge. And then in the products, we now see that the copper now has a 0 charge and the zinc has a +2 charge. So somehow the zinc has given up electrons. It's given up 2 electrons to the copper. There's a more formal way of doing this if we examine what we call the oxidation number. Oxidation number is a way of counting electrons on an element. So the oxidation number is an electron count relative to the neutral element. So the way we can look at this is we can develop oxidation numbers. And it turns out that the sum of the oxidation numbers of all the elements in a compound will equal the charge on the element, charge on the molecule. So for instance, in the sulfate ion, we can start to develop an idea of the oxidation numbers. What this says is that the sum of the oxidation numbers is equal to -2 in this particular case. But what are the individual oxidation numbers? The way we go about determining the oxidation numbers basically relies on a couple simple metrics that we can use to measure this. So an element in its native state, like zinc, would have an oxidation number of 0, sort of defined. Hydrogen would be 0. Each hydrogen would have a baseline of 0. For simple ions, the oxidation number would represent the charge. So hydrogen here would have a +1 oxidation number. Chlorine would have a -1 oxidation number. For more complex species, we have to tease out the oxidation numbers. Usually, when we see a covalent compound, we can base the assumption on the oxidation number based on a number of simple facts. Typically, hydrogen is a +1 oxidation number when it's bound in a covalently molecule. Oxygen is typically -2, and fluorine is almost always -1. Using these rules and other rules that we just showed, we can start to tease out what these are. So if this oxygen is typically a -2, we have 4 oxygens for a total of -8. Each of those oxygens has a -2 oxidation number. But all the charges have to balance. So the oxidation number on the sulfur would be +6. Because +6 plus -8 will equal -2, the total charge. So we can say that this sulfur has a +6 oxidation number. And you can do this for almost any compound. So take a look at SO3 minus 2 versus SO4 minus 2, the sulfite ion versus the sulfate ion. We see that using our rules that the oxidation number of the sulfur would be +4, whereas the oxidation state of this sulfur would be +6. Now for more complex things, metal ion containing species, we could isolate the oxidation number in each of these materials, and we find that the oxidation number for the iron would be +2, which is also analogous to its charge. And then we could do something similar. We see that the chlorine has an oxidation number of 7, +7, and the oxygen has an oxidation number of 2. The perchloride ion, ClO4 minus, total charge on this side, -8. Oxidation number of this would have to be +7 to balance it out. In many ways, it is analogous to what we did with determining the charge on a set of ions when we do our naming. Except these aren't formal charges. This is just a relative electron count. So going back to redox reactions, redox reactions involve changes in the oxidation number. Take a look at this combustion reaction. And while there's no obvious change in charge, if we look at the oxidation number, we see that the oxidation number of the hydrogens traditionally is +1. Again, I'm just showing the oxidation number of one of the elements of hydrogen. The oxidation number of the carbon in this case would have to be -4. The oxidation number of oxygen would be 0. And if we look at the carbon in the next compound, we know that each of those oxygens has a -2 oxidation number. And this carbon would have to have an oxidation number of +4. And we can do something similar analysis for the oxygen and the hydrogen of water to obtain the following oxidation numbers. What we can see is that in this case, the carbon has changed from a -4 to a +4 oxidation number. It's somehow managed to eliminate 8 electrons. Now, where'd those 8 electrons go? Well, it turns out that if you look at these oxygens, there's now 4 oxygens, each with a -2 oxidation number. They went from an oxidation number of 0 up to an oxidation number of -2. That would represent an 8 electron exchange. So that's a hallmark of a redox reaction. We're not going to deal too much with dealing with redox reactions this semester, but we should be able to spot a redox reaction based upon its number of electrons and the change in the oxidation numbers. So, precipitations, acid-base, and redox reaction. 3 common reactions. Precipitation reactions rely on solubility rules. Acid-base reactions, usually the presence of H+ and OH-, and then if you don't recognize it, it's probably a redox reaction. So look for change in the oxidation number.